Okay, so welcome to the lecture on electric fields. And in today's lecture, I want to basically answer one question, and that is, when I have an electron or a proton, let's say a proton, sitting here in space, positive charge sitting there minding its own business, and I bring another proton nearby, how does the first proton know that the other proton is there so that it needs to be repelled? In other words, we know very well that two particles with the same charge will repel one another. And the question I'm going to try to answer today is, if I have this guy sitting here by itself, and then I bring a second like-charged particle nearby, this one will be repelled. But it's very unlike a typical force where I walk up to a table and I kick it and the table moves. Well, in that case, we clearly see what's happening there. We see the force at work. It's a little more complicated than it looks. But, you know, in a macroscopic sort of way, we can see the force, we can get a sense for the fact that that table will accelerate after I kick it. But in this case, it's a bit more spooky. Here I have a charge, I bring a second charge nearby, and somehow they communicate with one another so that this guy knows the other one is here now and it needs to run away. That's a very unusual thing. And the answer was given by a fellow named Michael Faraday, who was an interesting, very interesting scientist, really considered probably the best experimental physicist who ever lived. And he came from a very humble background. Faraday grew up as the son of a blacksmith. You know, back in the days when in London, in England, I should say, there was a real class system. So he wasn't considered, a gentleman. He was the son of a blacksmith. And he was apprenticed to a bookbinder at age 14, so he didn't have a lot of formal education. Faraday finished his stint at the bookbindery right around age 20. And during the time he was in the bindery, he took a lot of the scientific books that came in and taught himself. He educated himself on the job. Very impressive guy. So he took and learned chemistry and physics while he was binding these books. By the time he was 20 years old, he attended lectures given by a fellow named Humphrey Davy, a whole series of lectures. And Davy was a very eminent chemist of his day. When the lectures were concluded, Faraday handed Humphrey Davy a compilation of the notes that he had taken during these lectures, along with his own questions on that material and his comments and so on. It was a few hundred pages worth of stuff, and Davy was very impressed, as you could imagine. And when Davy hurt himself in an accident doing chemistry in the lab, he hired Faraday to be his assistant. And before long, Faraday found a position at the Royal Society with Humphrey Davy, and it wasn't too long thereafter that Faraday's work eclipsed the work of Humphrey Davy. So toward the end of his career, Humphrey Davy was asked the question, what was your greatest discovery? And his answer was Michael Faraday. So very interesting fellow, Michael Faraday. Again, he's considered to be one of the greatest experimental physicists of all time. In fact, Einstein's office at the Institute for Advanced Study at Princeton had two portraits. One was of Faraday and one was of Maxwell. Both of whom we'll learn a lot more about this semester. But right now, I want to give you Faraday's answer to the question that I just posed. And that is, how does that proton know it has to run away from a second proton that I move nearby? And Faraday's answer was that this proton puts out something that we now call an electric field, and that field is present at all points in space. What you can imagine is that the proton, this charged particle, has changed the space around it in some way. And so we think about the proton as putting off this vector field that exists everywhere out here in space. I'll draw a few of the lines here. But we're imagining that every point in space around that proton is going to have the electric field that the proton is creating. So that if I bring a positive test charge, say right here, if I place a positive test charge right here, and I'll call its charge Q0, and the charge that's creating the field I'll call Q, well, Q0 is going to feel a force due to the charge Q. We already know that. We've studied Coulomb's law. But this is a way for us to think of how that force is being transmitted or mediated, so that when the charge Q0 is placed here, how does it know that it's going to feel a force and run away? It knows that because there's already a field in place, a field that was created by the charge Q. Okay, so this is just a basic idea of a field. We're gonna define the field mathematically here, or physically, I should say, as the force divided by the value of the probe charge that you put in there. In other words, it's the force between these two particles divided by the charge of the particle that's feeling the force. Not the particle that's creating the field, but the particle that's feeling the force. You can think of that as maybe like a probing particle or a test particle. We put that there, and oh boy, it feels a field, it feels a force, and it runs away. Okay? So the electric field is given the designation E with a little vector symbol above it because it is a vector field. And so this is the electric field. It has units of newtons per coulomb. Okay? This is the force, the coulomb, the force, the electrostatic and it's the net electrostatic force that's felt by the probe particle. Q0 is the charge of the particle that is placed within the field. And Q, although it doesn't appear in this formula, Q is the charge of the particle creating the field. Q is the charge of the particle that creates the field. Okay, so that's just a brief summary, kind of a motivation of, why of what an electric field is. Okay, a couple of things to realize about the electric field is that if I have a single particle that is positively charged, the field lines from that particle will always emanate radially outward. And I'll try to draw that as best I can here. But the field will be all the way through space, and it's radiating outward from the positive particle. Okay? So we call positive particles positive particles are sources of the electric field. They're sources of the electric field. The electric field emanates outward from those, from positive particles. Likewise, if we have a negative particle, now this is a negative particle by itself in space. Here's a negative particle. We say that the field lines for that particle are coming radially inward toward that negative charge. Okay? And we call negative particles, or negative particles, are sinks of the electric field. So we have sources of the field and sinks of the field. All right? Now, we also know that if we were to, and let me erase the board a little better here. Just take a second, make it a little clearer so that we don't have a lot of smudges on here. And we've looked at a single positive charge isolated by itself in space. We see the field lines emanating radially outward from it. Now, put that away somewhere. Now we put a negative particle by itself in space. We see the field lines coming radially inward toward the negative particle. Now the question is, what if we put a positive and a negative particle together in space? So let's say we have a positive particle here and a negative particle here. What does the field look like now? Well, we know that the field, we know that a positive charge is the source of the electric field. So the field lines are going to come out of the positive charge and they are going to be synced into the negative charge, like this. And if you look at my notes online, you'll see a very nice portrayal of this, much better than I can draw by hand. Very pretty. But that's not bad. That's not a bad rendition right there. Okay, so this is a dipole charge. We've got a positive charge and a negative charge together, and the field lines now look something like this. They're still emanating outward radially from the positive charge. They're coming into the negative charge, but the pattern is a lot more complicated than it is for either of the charges singly. All right? Now, what I want to point out here is, if I take a probe charge, a little positive probe charge, and I bring it, say, here, what's it going to do? Look at the positive probe charge. Now, it sees this big negative charge over here, and what does it want to do? It wants to be attracted to it. Okay, so does it just zip along in a straight line to here? And the answer is no. Why not? Because that's not the only player in town, right? There's also a positive charge here that wants to push it this way, and a negative charge pulling it this way. And overall, what does it do? It follows the field lines. Okay, so instead of just zipping toward the negative charge, it's going to follow the field line all the way over to the negative charge. And that's true if I put it, say, here as well. The positive charge is pushing it this way, the negative charge is pulling it this way, but in the end, the combination of the two the charge will follow the field line to the negative charge. Okay, that's how it works, and that's what we mean. That's a really good idea of why we think about electric field lines. It's a very easy thing to picture, and we can think about charges following field lines. Now, this board doesn't erase very well. Oh boy. Let me give it another dousing here. Okay. Now, let's say that instead of having a positive and a negative negatively charged particle in space, let's say that I have a little electric field machine and I turn it on, and so I have field lines being created, let's say, that look like this. And we'll see how to create a field. There really is no little electric field machine. I'm just making that up. Well, I'll show you a little bit later how we can create field lines that look like this. But I just want to reiterate a little bit what I originally said about the dipole, and that is, if I take a positively charged particle and put it in space here, it's going to feel the effect of these field lines, and it's going to accelerate in the direction of the field lines. Okay? Positive particles will move along the field lines. And the dipole example that I just showed gives you a reason why. You know, they're being pushed by the positives and pulled by the negatives, and so they're going to follow right along the field lines. If I put a negative particle in space here, the negative particle will accelerate opposite the direction of the field lines. So the positive particle will go with the field line, the negative particle will go against the field line. You think of the negative particle as a kind of subatomic salmon that's swimming upstream against the direction of the field lines. Okay? Just a couple of things to think about with field lines. When we drew the positive charge and we said the field lines are emanating radially outward like this, one of the things you need to know is the fact that when you have a higher density of field lines, that means the electric field is more intense in that region. A lower density of field lines means the electric field is weaker in that region. Now, when I say that, okay, I have a positive charge here in space, in a sense, I'm surrounding it with an imaginary bubble, you know, an imaginary sphere, and I'm looking at a little bit of surface area on the sphere, and I'm counting how many field lines penetrate that little surface. Okay, now you can see that you're going to have a higher surface density of field lines for this bubble than for this bubble. Therefore, we would expect the field to be more concentrated here than it is out here. I should say it should have a greater value closer to the charge than further away from the charge. Okay? And let's now see if we can calculate that and prove that that's the case. So what I'm going to do now is calculate the electric field for a simple point charge. I want to calculate the electric field for that example, where I have a point charge Q sitting here in space, and I want to find out what the electric field function is. So let's think about this. Let's say that I have that charge, that nice positive charge sitting here. It's a charge Q. And let's say that we know it creates an electric field around itself. Now let's say I have another positive charge sitting up here, a charge whose a particle whose charge is q0? Well, we already studied Coulomb's law, and we know very well that the force between those two particles, the magnitude of the force, is k times the magnitude of q times the magnitude of q0 divided by the distance between them. So here is the distance r between those two charges. And there's the force, magnitude of the force. Now let's calculate the field, the magnitude of the field. We said that the electric field is the force divided by the magnitude of the value of the test charge. Now, the magnitude of the electric field then would be equal to the magnitude of the force divided by the magnitude of the charge. But we know the magnitude of the force between these two particles, between Q and Q0. It's just this. So let's plug that in here. So this is K times Q magnitude times Q0 magnitude divided by R squared all over the magnitude of the test charge Q, Q0. And notice that the Q0 up here will cancel with the Q0 down here. Cancel, cancel, and out of that debris comes K, Q over R squared. Let me write that on a separate line because it's important. The magnitude of the electric field due to a point charge is K, Q, the charge that creates the field in the first place, divided by R squared. Here it is. The electric field due to a point charge. Now that's the electric field due only to a point charge. It's not good for, say, if I have, like you'll see in lab, let's say we have a slab of metal, a conductor that's charged. What's its electric field? Well, it's not this. This is only that situation. And let's look at this situation for a second. What does it tell us? What does this equation tell us? It tells us that the electric field depends linearly on the charge that's creating it. So if I have a huge charge, I'm going to get a big field. It also goes as 1 over R squared, so that as I go further and further away from this charge Q, the electric field is going to get smaller. And it's going to get smaller very rapidly because this is an R squared in the denominator. Okay? So if I have an electric field, at a distance of 1 meter, okay, if I go to 2 meters away from the charge that's creating that electric field, all of a sudden my electric field has gone down by a factor of 4 because I've doubled the distance, and since the distance is squared, the electric field E will become 1/4 of its original self when we were only 1 meter away. Okay? So that wholly corroborates what I said about field lines, the density of field lines, namely that in here we're going to have a stronger field than we're going to have out here. And this is telling us that the strength of the field varies according to 1 over the distance from the particle creating the field squared. Okay. Now, let's take an example, a conceptual example first. Let's say that I have a slab of plastic, something like polyethylene. Let's say I have a block of polyethylene, and you know that the plastic has all of these long chain molecules in it. And I'm going to just zoom our camera in on a couple of the molecules. And these molecules are, this slab of plastic and these molecules are in an electric field. Okay? And this is what happens. The charges in the molecules polarize. And we've talked at length about polarization of insulators. So I'm not going to go over that again, but just to say that if you recall, if I say have a large positive charge here and I have a neutral atom over here, the electrons of that atom are bound to the host nucleus to some extent. It's not like a conductor where they're free to roam through the material. If I have a big positive charge here and a neutral atom over here, the electrons of that neutral atom will spend more time on this side of the atom than on the other side of the atom. It's almost as though, the charge is being separated, but only by a certain amount. And that's what we're seeing here. These molecules are being polarized by an external electric field, and they end up stretching the molecules end up stretching, with part of the charge on one side and part of the charge on the other side. Now my question to you is, what is the electric field direction inside each molecule? Let me give you just a second to think about that. The answer is that the electric field goes from the plus charges to the minus charges. So the electric field lines are in this direction, inside the molecule. Okay? So this is what it would look like. And how do we know that? We know it because electric field lines always emanate outward from the positive charge and they terminate on the negative charge. So that's what we're seeing in each of these cases. Now the question becomes, how did these things get polarized in the first place? Well, we put the block of plastic in an electric field. And I ask you, what is the direction of that external electric field that caused the polarization of these molecules in the first place? What's the direction of that field? Let me give you a minute to think. Okay, and the answer to that is the external electric field lines have got to look something like that. Why? Well, because we know that the negative particles went that way, and the positive particles in each molecule migrated this way. So, what do we know about electric fields? We know that if we put a positive charge in the electric field, it'll go along the field lines. That's just what these positive particles in the molecule did. They went from being sort of central to the molecule to stretching this way, while the negative particles went this way. And we know that negative particles always move against the field lines, while positive particles move with the field lines. And that's how we know that the electric field external to these molecules, the electric field that this hunk of plastic is bathing in, the electric field must be going that way in order to cause that kind of polarization. Okay, now let's do a quick and easy numerical problem, just so that we get to plug some numbers into the electric field.